Hey gang, okay, so hopefully you've messed around with that worksheet once, at least once, hopefully a little bit more than that. But while I am going to draw a mechanism, don't shudder, in this video, this is more, at least at Pitt, I wasn't required to know the mechanism. I just had to know how to use the Wolff Kishner reaction, but I was shown the mechanism, and kind of to be a little nerdy and nostalgic, a little emotional, when my Organic Chemistry 2 teacher, Dr. Nelson, showed me it, I was like, damn. And I really feel like that was one of the first moments where I knew I had to do something like this with organic chemistry and help others learn, because I just thought this was so cool. Okay, so what is the Wolff Kishner reaction? If you look up here, I just gave you a generic carbon, but it can be, or carbonyl, but it can be any carbonyl. It could be this carbonyl, it could be a cyclohexane carbonyl. Any given carbonyl, if you subject it to this amine right here, this NH2 or NH2 and H2O, and a second step of H2O and hydroxide, aka give it a basic environment, then you will just go ahead and wipe away any carbonyl. Remember that reaction with benzene where we did H2PDC and it wiped away that benzylic carbonyl? This will wipe away any carbonyl. So let me show you the mechanism, and then I'll show you kind of some complete the reaction examples. This is going to be a short video. Okay. What's kind of cool about this mechanism is that it goes through imine formation. This first step right here has some acid and a loss of water involved. So I'm going to draw you guys the full thing, because it's never a bad thing to see this mechanism happen more and more. Okay, so if we have our carbonyl, remember the first thing we need to do is activate it, and the best thing for us to do there is to protonate it, right? So we'll grab H+, we'll protonate our carbonyl. That means we're going to activate him. Alright, from there, we're going to enter in our amine, NH2, NH2, doesn't matter which nitrogen you pick to go in and attack, but we're going to attack with one of them, kick these electrons up. Then we're going to have our intermediate, where we have OH to the left, we have the nitrogen piece to the right, sorry about that. And then remember, we need to play the game of, we want to protonate the things we want to get rid of, we want to deprotonate the things we keep, right? So I'm going to use some hydronium right here to protonate the oxygen. And then I'm going to use some water to deprotonate the nitrogen. Remember, that's our proton shuffle step. You just draw that, give you a good look at it, right? Protonate the things we want to get rid of, deprotonate the things we want to keep. I know this is old hat for you guys. So we have water over there. We have our amine piece right here. Okay? So the way we'll kick off water is we'll swing our electrons down, form a double bond, form that imine, drive off water. Remember, minus H2O. That's going to help us get a good entropy effect going. Then we have this type of imine. One more step to clean him up. We'll recover our catalytic acid, right? And, right, so I'll put the H3O plus up here just for accounting purposes, just to make sure we have him. But now we've formed our imine, right? Up until here, you guys could have done this no problem. So here's kind of where things get a little different, and here's kind of, you know, how the Wolff Kishner reaction proceeds. Sorry, I just wanted to expand that. So now we're switching over from an acidic environment to a basic environment, right? So I'm going to draw some base. Here's what's going to happen. We're going to deprotonate this nitrogen with one of these. This hydroxide is going to grab one of those hydrogens, one of those protons. And then we're going to throw them, the lone pair on that nitrogen. The following result from that electron flow. We didn't touch that double bonded nitrogen. Here's a lone pair right there. And now we have this nitrogen having two lone pairs and a negative formal charge. Okay, so here's what's going to happen next. And just follow me on this, because there's going to be some type of payoff at the end, okay? So I'm going to swing these electrons in here to form a double bond between the two nitrogens, but I have to move a pair of electrons in this double bond, otherwise this nitrogen is going to break the octet rule. So what I'm going to do is I'm going to kick it up as a lone pair on that carbon right there. So let me draw the result of that electron flow. Start drawing down here. So we have a lone pair on the carbon down there. Single bond between the nitrogen and that carbon. Double bond between the two nitrogens. That one nitrogen has a lone pair. The other nitrogen still has a lone pair. And we have that hydrogen right there. So here's what's going to happen next. This carbanion is not going to stick around. We're going to grab a proton from water. Let me grab that. Draw that right there. Little acid-base reaction. Okay. So we're going to basically do the same thing over again. We're going to deprotonate this nitrogen. We're going to take away that proton that he has right there. We're going to introduce another hydroxide. We're going to grab H plus off of him, and we're going to dump those electrons onto that nitrogen on the end. Draw the result of that electron flow. Alright, so now he has two lone pairs and a negative charge, and that's where we stand. Again, I'm going to swing these electrons in to make another bond, a triple bond right there. And here's the crazy part. I'm going to take this bond right here, I'm going to break it completely and dump a lone pair onto that carbon. And that seems crazy, right? But think about this. While we do produce this, lone carbanion, think about what else we produced, right? Remember, nature likes stability. We produced N2 gas, right? N2, nitrogen, diatomic nitrogen, is so stable. That is a totally awesome payoff, okay? So once this happens, all we need to do is have him grab a proton from water, and we're done, right? So all we got to do is grab that H right there, and this is how we wipe away that carbonyl. So the Wolff Kishner works through making an imine. Then you have to deprotonate a nitrogen a few times. You end up producing N2 diatomic nitrogen gas, and you get the payoff with your plain old alkane. So it doesn't matter what you have. If I have, just say, some type of cyclopentanone, and I use the Wolff Kishner reaction, this is what I'm going to end up with. You just completely erase the carbonyl. Okay, so like I said, I don't know if you guys need to know this mechanism. I knew it. I just kind of liked it. I thought it was cool. I know it's extremely nerdy, but all you need to know is what it does. You might need to know it for a synthesis reaction. It's a super simple one, right? Not hard at all. All right, we have one more video with carbonyls. We're going to tackle a reaction called the Wittig reaction. It's kind of cool, a little kind of complicated, but we're going to step through it and make sure we can handle it.